Either you have a doubt or you don't have a doubt. That was my question. Just reply it. No, sir. Yes. But you are hearing and you are not giving reply. What I mean? Okay. So, Gokul, can you see the screen? Please
Yes,
respond.
sir.
Are you able to
Yes,
see
sir.
the screen or not?
Yes, sir.
And what we are going to do here is, here we have example of modeling radiation and natural convection. We have an example of modeling radiation and natural convection. Convection is two different mediums from one body to other body. There is a natural convection which is going to take place. First, I'll show you the object, then I'll read the description of the object. So here we have an object. Okay, so this is your heating surface. A heat wall is which is a temperature of 473.15 Kelvin. This is the heating object. Now it is getting conducted from this phase to the other phases, and they have given the parameters of this block. So what we are going to predict is, we are going to predict the each and every other five phases, other five except this heating surface, other phases, how much heat is getting conducted, what is the heat flux, that all parameters we are going to calculate in this using with a different model. So what is the object is to compute the flow and temperature patterns in a box as well as heat flux. What do you meaning of heat flux? The amount of heat transfer per unit cross section area. So that it is define the heat flux using surface to surface model. There is a model which is present in the Ansys Fluent using a surface to surface model available in Ansys Fluent, and using combined radiation and natural convections are solved in three-dimensional square box on a mesh consisting of hexagonal elements. And what you are going to predict using surface to surface and radiation model in Ansys Fluent, set the boundary conditions for heat transfer problem involving in the natural convection and radiation, and calculate the solution using pressure based solver, and display the velocity vectors. And this is important, we are going to display this. Okay, this important, uh, display the velocity vectors and counters of wall temperature also we are going to predict, and also we are going to find the cluster surface cluster id. Okay, each surface how much heat flux it was there and what is the radiation from each surface, that is also going to predict using cluster id, and also radiation heat flux. So I'll read the problem. Okay, so a three-dimensional box which is having length, breadth and height of 0.25 meters, and hot wall of aluminium. So they already mentioned the aluminium of at a temperature of 473.15 Kelvin, and all other walls are made up of insulation material are subjected to radiative convective heat transfer to the surroundings. All other walls are made up of an insulation material. They have mentioned that is an insulation material. Okay, and subjected to radiative and convective heat transfer to the surrounding temperature of 293.15 Kelvin, and they have mentioned the Prandtl number approximately of 0.71, and Rayleigh number is based upon the length, that is of 0.25, which is having 1 e power 8, and the Planck number is 0.3006. So these are the inputs they have given here. And there is one important parameter we have to see. Yes, here we have a view factor. What is the meaning of this view factor? So anyone please tell me what is meaning of insulation? Anyone, what do you meaning of insulation? What do you mean of that?
Uh, to prevent heat loss.
To prevent heat loss. Good answer. Yes, so to prevent heat loss we are applying insulation to the all other phases except this heat body. We are giving insulation to the all other five phases. Now even we also giving a we also giving to surface to surface, we also giving a the other layers, we are being arranging a surface to surface clusters we are going to arrange. Okay, what do you call, we are going to arrange some clusters. Even no, what do you meaning of this clusters? The same thing, it is going to act the same principle like insulation. So what we are going to do is, we are going to apply some clusters to this, uh, I'm going to arrange some clusters to this all these faces. Okay, the same similar faces, I'm going to apply some clusters in order to avoid the heat loss. Okay, so like 10 clusters, 20 clusters we are going to apply here. Okay, so we are going to apply the clusters like 10, 20, like continuously series of clusters we are going to apply here. Like series of clusters we are going to apply over this face in order to avoid the heat loss. Continuously 1, 2, no, this is one cluster, two clusters, 3, 4, 5, 6, 7, 8, 10 clusters, it is going to be applied. Why, sir, why we are applying the clusters? What is the main advantage of clusters? The clusters are useful to we are avoiding the heat loss. Okay, we are not passing which is heat, no, which is transferring from this phase to other phase, which is getting conducted. In order to avoid the heat loss, we are applying clusters. Sir, already we have given insulation. No, what is the need of applying clusters? Even we are applying clusters to check the how much heat is getting radiated, what is the heat getting transferred, that we want to predict. Okay, so that we want to calculate using this clusters example. Okay, so view factor, the model what we are using is Ansys Fluent is surface to surface radiation model, can be used to account the radiation exchange to the enclosed gray diffuse surfaces. The energy exchange between two surfaces depends upon their size, okay, separation distance and orientation. So these parameters are accounted by a geometrical function called view factors. For most of the applications, the surface is a question of OPKU to the thermal radiations in the infrared spectrum. So surface can be considered as a OPKU surface. For gray diffuse and OPKU surface, it is valid to assume that emissivity is equals to 1 the absorptivity, and the reflective is equal to 1 minus the emissivity. So first, on what basis you will calculate this emissivity and reflectivity? So black body is a perfect absorber of heat and perfect emitter. If you see, if you have a black body, definitely whatever the amount of heat is observing, the same amount of heat is going to be reflected. So how you define this emissivity? 1 minus the 1 minus the black body, you can take the emissivity. So approximately when it is equals to 1, that we call as black body. So if it is less than the black body, emissivity will be less than the black body. So how you define this absorptivity? Emissivity is equals to absorptivity. So reflectivity is equals to 1 minus the emissivity. Okay, how you define this reflectivity? 1 minus the emissivity. Well, how you define this emissivity? Emissivity is defined as, which is approximately, if it is equals to 1, that is a black body. If it is less than 0 0.7, 0 0.8, that will be emissivity. Okay, using these values, we are going to assume and we are going to calculate the problem. Okay, so then I'm going to open the application. So go with okay, so fluid flow fluent. So here I'm going to define this as modeling radiation and natural convection. I'm going to take this. Now out of this, I'm going to browse this mesh file, right click, import, browse. I'm taking this radiation box mesh, I'm going to take it that. Then you can save it. So from here I'm going to set up. So I'm using double precision. Sorry, use double precision. You can go with that. Can I'll show you the diagram again. So what even they have given the gravity, and aluminum is one metal and insulation is other metal. Two metals we are going to take it. The temperature is 470, heating wall, and rest of the things are 293.15, the ambient temperature which is having. Okay, just try to fit to the screen. You have this. Okay, so this I'm going to use it. Now go with the gravity. So along which side? No, along in the y direction. I'm going to define this gravity, which is of minus 9.81. I'm going to use that is pressure based absolute steady state. You can just check the quality of the mesh and report the quality. Yes. So first what I do is I'll make you to understand they have given some named selections to this 6 walls. Sir, what is that? So you can remember that using with you remember that with respect to this coordinates. So when it is positive x, this is a positive x, and negative x, and positive z, positive negative z, positive y, and bottom is negative y. So you can remember that. So first one is high wall x, which is high wall. I mean no. Uh, High wall x, that is a positive direction, that is the space. Try to display it. High wall, I'm going to take high wall x. So this is your face. Okay, high wall x, and high wall low x. So I'm going to take it this other side. Okay, the positive direction is high and negative direction is low. Okay, so next one is high wall y. High wall y is the top one. Try to display that. And high wall low, no, you can take it this bottom. And wall high z, I'm going to take it this, and wall low z, I'm going to take it this. Okay, so this we have. And the interior mesh we'll have it, right? So I hope you understood which is wall ix and wall y. Because why, sir, why you are making to understand? Because we are giving the boundary conditions to this cases, wall high y, wall low z, we are giving the parameters. Okay, so now once we're done, try to close it. So temperature is the important parameter, right? Temperature we will calculate, so then you can enable this energy. Okay, so try to give energy is important parameter. So once we give it that, now using radiation model, right? So how we can know go with a radiation model? So in that you can go with here surface to surface radiation. From one surface to other surface, we are going to do that. Okay, so in that go with clusters. As I said, no, clusters are a type of opposing, no, which are which will not emit their heat to pass outside. So that we can call clusters. Go to the settings. So how many clusters? First time I'll show you the clusters. I'm going to apply one cluster. Default I'll go with one cluster. Try to apply to all other walls. Okay, so apply to basic surface to surface, apply to all walls. Try to give OK. And you want to save that clusters. Sir, why you are saving this cluster? Because I want to compare the results. I want to compare this, so that's the reason I'm just saving this results. Compute read.data. So where you are saving? So in the desktop, I'm saving in a folder where you can remember that. Now you can create a folder over there. Clusters. Cluster. So here I am going to take it. Put it as one. You can put it as one. Okay. It is going to save that clusters. Okay. So it is going to be saved. Right. So I am going to give OK. 100% it has been saved. Sir, can you show me that folder? Yes, you can see it. No, the folder you have the clusters. So it has been saved this. Okay. Radiation box 1. It has been saving here. So try to close it. You can go with this. Okay, so now what you can do is I'm going to create two metals. One is aluminum, one is insulation metal. So yes, energy we have given, and radiation surface to surface model. Go to the material. So here we have only, air we have, or aluminum, we have aluminum. So what you do is create or edit. Okay, so I'll go with create or edit. So you can put it this as, change the name, insulation. Sir, I'm not editing this aluminum, because if I give change or create, I'll be giving no. Okay, both will be there. Aluminum will be there, insulation will be there. Okay, insulation, just rename it. Okay, what are the properties of that insulation material? So I'm going to give the properties of that. That is of 50 density I'm going to give. Please note these values, because in the, what do you say, in the PPT it is not mentioned the properties of this insulation. So the specific heat is 800 joule per kg Kelvin. Thermal conductivity I'm going to give 0.09. I'm going to use it this. Okay, so that I'm going to use it. So change or create, I'll be giving no. If I give yes, what happened? The aluminum is going to be edited. Now I'm not going to give yes, I'm giving no. So both insulation will be there, aluminum will be there. Okay, so this insulation, this is the insulation, and this would be, aluminum. Both will be there. Okay, now it is an incompressible air water. No, go with edit. So in that you can change the parameters. Okay, so density is incompressible ideal gas, I'm going to take it here. So specific heat I'm going to give it, that is of, you can change the values. The air I'm going to use approximately 1021 joule per kg Kelvin, I'm going to take it here. Okay, please note these values. Sir, I want to go with the default values. You can go with the default values, but as per my results, I want to achieve my results, then have to change these values. Okay, so thermal conductivity I'm going to use it 0.0371. I'm going to use it. Okay, and viscosity of that I'm going to give is 2.485 e power minus 0.5. I'm going to use it this. Okay, so what you do is change or create, you can go with that. So that I'm going to use it. Try to close it here. Right, so air we have changed it, and insulation we have changed this parameters. Right, so once we define it, so we have to define, now we have given insulation, we have to assign it. So which is your heating object? This is wall high x, no, wall low y is your heating object. So that I'm going to give cell zone conditions. What you are going to give in the cell zone conditions, which is already air was there, no, which is already air was there, I'm going to use that. So next go with boundary conditions. So I'm going to take it wall high x. Okay, wall high x I'm going to take it. First I'll go with wall high x, then I'll go for the other object wall high x, go with edit. Okay, so go with edit parameters. In that, go with mixed combination of radiation heat flux. I'll go with the mixed, because radiation, convection, temperature, heat flux also I'll go with mixed. So here heat transfer coefficient, so I'm going to use it watt per meter square Kelvin, that is of 5 watt per meter square Kelvin, that is heat transfer coefficient. Please make a note. And free temperature, how much it was there, so which is of 293.15 Kelvin, I'm going to use it that 293.15 Kelvin. And external emissivity, which is having 0.75, that is 75%. So this is like, 300 radiation temperature. And internal emissivity I'm giving 0.95. If it is equals to 1, that is black body. Okay, so what is the wall thickness? You want to define the wall thickness, I'm going to give the wall thickness as 0.05. I'm going to use it. Okay, and the material is insulation material. The material is insulation material, I'm going to use it that. So try to give okay for the condition. Right, so next is the opposite side, the wall low x. Wall low x, or what you can do is, because the same temperature we are giving, right, because see every walls are same, no, every walls are same, but what I do, instead of giving again go with wall low z, wall high z, if you're giving that way, it will take me a lot of time. Whatever the inputs you have given, I'm going to copy to other faces also. Go with copy conditions, from where you want to copy. So from wall high x, this is a wall high x, copy to which faces, wall high z and wall low z. I'm going to copy this z coordinates, I'm copying this. Okay, so then you can try to copy that. So you want to give it okay, yes, I'll be copying that and try to go with this. Okay, so once again, now our heating object is wall low x, the other side, wall low x. I'm going to take it, go with edit. Please, any doubt, please let me know. I'm ready to help you. Temperature, thermal, because that is 473.15, 473.15 Kelvin. It is not equals to 1. If it is equals to 1, that is a black body. Internal emissivity is, I am going to take 0.95. Okay, so I am going to give it here. So try to give okay. That is aluminum metal itself. It is not insulation. Hot body is aluminum metal. I am going to give that boundary conditions. The next case is wall high Y. Wall high Y, you can take it, edit it. So in that you can go with here thermal, go with mixed. So in that you can give the values, that is of heat transfer coefficient, which is of 3, and you can go with the free stream temperature. I'm going to give 293.15 Kelvin, and external emissivity is of 0.75. I'm going to use it, and radiation temperature, which is having 293.15 Kelvin, and internal emissivity that I'm going to give 0.95. I'm going to use it, and wall thickness, that is of 0.05. I'm going to use it this. Okay, so once we define this, then you can go with okay, go with okay conditions. So no, it is insulation material, right? Put it to insulation material. It is not aluminum, it is insulation material. Heating object, right? No, it is not heating object, it is an insulation material. Okay, so next case is give okay, right? So here you can see the description, right? You can have hot wall is of aluminum, all other made up of insulation material subject to radiative convective heat transfer. That's what we gave it. Now what I do is I'll go with copy conditions from wall high Y, wall high Y. So copy to wall low Y. I'm going to copy this. Okay, just try to copy the condition, giving okay. Right. So this way how we have. So once we define, try to close it this module. Okay, you can close it here. So this we have given. Now I'm saving this results. Using pressure based, it has been solved. So go with the dynamic mesh and reference values. You can know. I'm not going to use any reference value. You want to cross check, you can cross check that. Solution methods, I'll go with coupled solver. Again I'm using CDO transient. Okay, using coupled based solver, I'm going to use it. So solution controls, I'm not going to change. Monitors, so you want to calculate, you want to calculate any regions you want to calculate, you can calculate it. Okay, so second calculation activities, energy is second order. Okay, let it be second order, and I'm going to use monitors. So which area, first we will initialize this inputs, then we'll go with the hybrid initialization itself. I'm going to initialize it. Okay, one or more cells equidistance from specified reference. Okay, because we created only one plane, right? Not a problem. One or more cells is equidistance from specified reference pressure location. Okay, one is fine, right? So then once you create, so what is my intention is, see, I can see the temperature and all that stuff, I can see that, but what is my intention is, I'll create a plane exactly, with respect to z axis. I will create a plane over here. So at that middle plane, I want to see the temperature. Sir, without that plane also, can I see the temperature? Yes, you can see that. My intention is to create a plane exactly in the middle of this block. I can see, I want to see it there. No sir, I want to see the temperature over here. You can also see that. Okay, because in the middle you have maximum, right? So that's what I'm seeing it, maximum convection going to be happen. So that I want to see it here. Sir, how do I create a new surface over there? Go for surface, you can go with your new surface iso surface. You can create it. Which location with respect to mesh along z coordinate? I'm going to take it here. Z coordinate, I'm going to take it z coordinate. So you can go with here. You can go with here with the location of 0. So you can give the name. So like along with respect to z coordinate we are creating, right? Z center. Why sir, why you're giving this way? Because you can give any name, man, that is not a problematic. Okay, with respect to z coordinate I'm going to create it. Okay, or with respect to value of 0 I'm trying to create it, right? It is going to be created. Sir, can you show me that? No, here you can see. And what I do is in the general you can go with the display, except this, I'll go with here z new plane. No, this is your low z and high z. You exactly you will have middle, right? This is your new plane. This area I want to see the temperature. Okay, that is my intention. So go with here, already we initialized it. So then once you done it the new plane, so go with calculation activities. In that you can go with here how you want to create monitors. I'm going to create a surface monitors over there. Okay, so create the surface monitors. So what you want to create it? I want to see that temperature. Okay, what it new surface at zz center or zz middle surface, this area. So what you want to see, plot that too also I want plot, even I want to write that also. What you want to see? So I'll go with area weight average. You can find it average. Yes, area weightage average. So what you want to see? I want to see the temperature at which center, at exactly in the middle long we have created. So that I want to see it over there. So try to, okay, this area you can plot the graph. Apart from this, already you will get a graph of this no velocity counted continuity equation, x velocity, y velocity. Even this also going to be plotted. No sir, I don't want to have. You can put it to none. Okay, so I'm just giving no. So then what you're going to do is I'm going to run the calculations. Go for run the calculations. For approximately I'll go with run the calculation for 300 iterations. Okay, 300 iterations I'm going to calculate it. So just try to calculate it. No, this area, which area is having no static temperature at middle surface, how much it was having? Approximately 473, 473, 472, 473 you have over there. Can see 472, 473, approximately half 473 over there. And rest of the things, how it has been changing. Usually temperature won't get converged. If you see, temperature will not get converged. Not a problem. If 300 iterations, we can proceed it. Okay, so even it is not get converged, radiosity converged at 3 iterations. You can see this radiosity converged at iterations, but no, the temperature is not get converged. So final radiosity is at 1.4. You can see. So just try to give it okay. So I want to see the results. Okay, so go with even we can see the results even it is not converged also. Go for graphics, counters, setup. So I'm going to use which region, because at the center region, right, I want to see. You can just go with here, change type to temperature at this area. So you can try to plot it. You can see there how you have. So even you want to put it instead of auto range, you can put it here, 421 to 473.5. You want to see that, you can try to display that. Okay, so this way we can plot it. Now my intention is to plot a graph. My intention is, so we can plot a graph. Before plotting that, I want to see the total surface of the object. I want to see the total thing. Just try to enable it. Okay, just try to enable all this. So you can just enable all this except this, the interior mesh. Okay, why sir? Because interior mesh we cannot see that, but the outer surface I want to see, try to display that. Okay, we can have the whole object. Okay, so we can have it how it has been. See, and how we have, how temperature is getting involved, we can see it. So clip to range, it was there, you can undo this, you can go with that, right? This way we can have, this is your heating substance we have. Now what is my intention is, I want to plot a graph. Okay, so I want to plot the graph. So how do I plot a graph? So before this, how we can plot it. So I want to create a line exactly in the top of this. I want to create using that line, exactly of that, or in the middle of this I want to create a line. So using that line I want to plot the graph. So how do we create a line? Go with surface, line or rake, you can take it this. Okay, because this distance is how much we know the distance is 0.25 meters, using taking the values as consideration. Exactly it x distance I can go with minus location 0.125. okay, and this is at 0.125. y 0 and z is a location of 0.125, and this is 0.125. so this region I'm going to plot it. Okay, so what line, you can give line z, any name you can give for your identification. ZZ line I'm going to create it. ZZ line I'm going to create. Okay, ZZ line site, you can try to create it there. Sir, can you show me that line? Yes, so in the display you can go with here, the line was there, no, you can only display only that line you can display it. So this is your walls, exactly in the middle you have that, exactly you have over there, right? I hope you can see this line, right? So using this line I want to plot the graph. Okay, so how do we plot, and rest of the things also you can plot it. Okay, and you want to see that wall temperature and all that stuff, you can go with the graphics, counters, setup, what you want to see that. So I want to see the wall fluxes, you can go with your wall flux. In that you can have wall shear stress. Okay, so radiation heat flux, you know, radiation heat flux, which region, no, even line also you can select it. You can try to display that how much radiation which was there. Based upon that you can see radiation heat flux. Okay, so now like vector displacement, there is other type of representation you want to see that. So go with here vector representation setup. So what, no, velocity display representations, velocity at which region, at this region, try to display it. You can put it in the z coordinate. You can see the movement of, you can increase this arrow size. So how do you can put it to 5 and try to display it again. You can see the movement of, you can see how the, happen. So there is other representation also. I want to see that. So path lines, you can see that. So you can try to variable. I want to see the temperature variable. Which region, at this center region, you can display that. Because it required a lot of graphics. See how it is, So these are the path lines. So you can decrease the step size to some 150. Display. And you can pulse it. The movement, how it is being getting. You can see, right? It is a one type of animation you can see. Okay, so I'll just stop it this, but don't select all these phases because it required a lot of graphics. Only the middle phase have been selected. Try to close it. Right now, sir, you said no, sir. Can I see for each and every phase's temperature and all that thing? Yes, you can also see that reports, fluxes. You can go with that, or you can click on reports, fluxes. You can create it. So which region? So what you want to see the results? I'll go with total heat transfer rate. Okay, the total heat transfer rate. It no wall low x is our which one? Wall low x is our heating object, right? What is the heat transfer rate over there? You can see that. So which is having 59.54 over there. Okay, you can see for individual phase heat transfer in terms of watt. Okay, so this is one way. And next cases, the other important cases, I want to see for radiation from all the phases. You can go with here. You can select except. You can select all except the interior. Even we can now you can see that. So how much which is having the radiation which is having, which is 0.23 which was having over there. Okay, so no sir, only the particular phase, the heating object, from the heating object how much we have. No, I'll go with your radiation from the heating object. This is wall low x is our heating object, right? Just try to compute it. So how much it was there on the heating object, the radiation is 49.24 you have there. Okay, so we can see, sir, I want to plot the graph, sir. You can see mass flow rate. Now mass flow rate is not required because we are not calculating with respect to mass. Heat transfer rate and radiation heat transfer rate, you can see that. So try to close it. Right, now this time I want to plot it. So how do I plot? Go with plot, xy plot, or you can go with here no, plot itself, define, or you can go with here display plots. Can have plot. Okay, display plot. So xy plot. So which region I want to plot the temperature with respect to wall temperature. I want to see that at which region. So at which we create a line, right? That region I want to plot it. You can plot it. So how the temperature was there. Okay, so that region how the temperature was there, you can see that with respect to, even with respect to distance also 0.125 125 because we have line was exactly in the middle, right? So it will taking from this distance, right? So this way you can plot your graph. And what I'm saying is, once you plotted this, you can write this file. Okay, just write it. So where in the desktop, in the Fluent, so in the cluster, or what you do is you can create a new folder that is of graph. You can put it as a graph. Okay, just put it here. Now this is for You assume that this is for cluster 1. Cluster 1. If you apply cluster 1, what is the graph? A cluster of what? Temperature. Temp you can give. Cluster 1 temperature you can give it here. So it has been saved here. Now, and the second case with the line of same line, after changing again you solve it. So here you can the models no go with radiation, and here settings, then you have to put for clusters of 10, 10, 20, 30, 40, 50, up to 50 you have to do, up to 50 you have to calculate it. So first I solve for 1, you have to put it 10, then you solve it, again you plot the graph. So put the value 10, okay, and just give okay. Now what you do is again you solve the problem with the same inputs, calculate, then again you can go with plot, xy plot, okay, then again with line and just try to plot it, or you write it, or you can plot it, write it that. So then what you do is the both files will be there, no? For example, you have, I'm just, instead of write, I'm just plotting it, okay, you are plotting this. So I'm writing this, so write it. So this time in the Fluent, desktop, Fluent, graph. So you change, clusters of 10, cluster 10, cluster 10, temperature graph, no? So you have this two files will be there. So what you do, you want to compare both of them, so go with file, no, just double click on this file, add the files, okay. So in the desktop, in the Fluent, graph, you take this two, this and this, you take it first, you take this, okay. Already in the previous, yesterday we were added, no, you can just delete it, and this also you can delete it. Again you take the first one, okay, you take the first one, you add it here, no, first one, this is the first one, add it again you take this second one. So both will have, no, both you can plot it, both you have plotted, both are same, right? We have not calculated it, okay. So that's the reason showing one thing. You can see the graph, definitely you will be changing, the graph will be, you will get the change. Understood? What changes you've been observed, you have to tell me that. Will you do this? No
Yes, sir.
question, no answer, no nothing. Just please respond, man, so that I can also communicate with you. If you have any doubt or something.